Okay, we're starting with 619. I'm going to go kind of fast because I'm trying to get to the meditation service tonight. Part A, it says on 619 to use the patterns you have investigated to determine the missing side lengths of each of the triangles below. So these might be 30, 60, 90 triangles, or we might be looking at some triples here. Well, this is definitely going to be a triple because I don't know the measures of these two acute angles, so it can't be a 30, 60, 90 or a 45, 45, 90. So it must be a triple. Triples are just common lengths of right triangles. That's all that it is. And once you use them enough, you start to remember them. So if you feel a little overwhelmed right now, there's a poster in the room with them on it. As long as you recognize them and can identify it with the poster, you're probably going to be able to find the missing side. This part of the test will be timed, and you won't be able to do Pythagorean theorem. You will need to use the triples. So if you're looking for a strategy, how do I figure this out, miss? You know, I'm looking at this, the first instinct is going to be to use Pythagorean theorem. Look for a common factor. If you can divide by the greatest common factor, then you are going to, also I would recommend writing a squared plus b squared equals c squared. So you know 20 is your hypotenuse, and then 12 is one of your sides, and you're trying to figure out this side over here. Okay, well, I'm going to divide by 4. Both of these are divisible by 4, and that's going to give me 6 and 5. Okay, and and 20. Oh, sorry, where did I get 6? I'm like, what is this going on? Okay, so that gives me 3 and 5. So then I'm going to look at my poster and see that I have a triple lengths 3, 4, and 5. So this is just a dilation of a 3, 4, 5 triangle. That's the most common right triangle that you have. So I know this is a 3, 4, 5 triangle, and this 12 is 3 times 4, 20 is 5 times 4, so I'm just going to do 4 times 4, or I could say to myself, what divided by 4 would give me 4 times 4 is 16. Or you could just say, what divided by 4 would give me 4, so it would be 16. So you're looking for these particular triangle lengths, side lengths, when you're looking for a triple. And I'm only going to put ones in the test that are multiples of these. I'm not going to put some more uncommon ones. There's plenty of them. There's an infinite amount, but let's just focus on the most common. Okay, part B, we've got a 45, 45, 90 triangle. So we know that the two legs are going to be the same. So this is going to be 15, and I'm just going to use my pattern. The hypotenuse is going to be 15 times the square root of 2. Hypotenuse in a 45, 45, 90 triangle is always the leg times the square root of 2. Okay, C, we don't have any angle measures for the acute angles, so this is a triple. Let's divide by the greatest common factor. So the largest number that goes into 10 and 26, I'll put the 10 here and the 26 here, is 2. So let's divide by 2. That's going to give me a 5 and a 13. Okay, so I'm going to look at my poster. 5 and 13, 5, 12 and 13 is a triple. So then this must be a multiple of 12. This must be a dilation of a 5, 12, 13 triangle. And 12 times 2 is 24. 13 times 2 is 26. 5 times 2, so 12 times 2 is 24. Or you could say, what divided by 2 is going to give me 12? So that's got to be 24. Let's see, D, we have a 30, 60, 90 triangle, and we have the hypotenuse. So remember, in a 30, 60, 90 triangle, the hypotenuse is double the short leg. So this is double this short leg right here. If you were to reflect it over the long leg, that would be an equilateral triangle. This is 30, this is 30, so then this is 20. All of this would be 20, so just this short leg would be 10. And then the long leg is the short leg times the square root of 3. So this is going to be 10 square root of 3. Okay, 6-20. Okay, it says to solve each equation by first rewriting the expressions in each part with the same base. Okay, so we have 8 to the x equals 2 to the 6. So you want to say to yourself, what power of 2 would give me 8? Well, 2 times 2 times 2 is 8. So 8 is 2 to the third. So this is 2 to the third raised to the x power. And we're trying to figure out what x is, if that is equal to 2 to the 6. So remember, when you're raising a power to a power, this is leading into what we'll be doing in the next couple of lessons. You're going to need to know all of your laws of exponents. That means that when you're raising a power to a power, you multiply the exponents. So 2 to the 3x equals 2 to the 6. Okay, so that means 3x must be equal to 6. If these have the same base, and 2 to the 3x is equal to 2 to the 6, and 3x must be equal to 6, and x must be equal to 2. Okay, let's try part B. So 9 is 3 to the second power. So we have 3 to the second power for 9 raised to the second power equals 3 to the 2x plus 1. So that means 3 to the fourth power equals 3 to the 2x plus 1, which means 4 equals 2x plus 1. Solve for x, subtract 1 from both sides, divide by 2, so x is 3 over 2. Okay, part C, 4 to the 2x equals 1/2 to the x plus 5. So remember, I need to save this page. In the last video, we looked at this pattern to figure out what negative exponents mean. And 1/2 is 2 to the -1 power. If you don't know why, you should watch that video. It was for 6.6 through 6.11. I think it went with number 9, maybe 6. I don't know. Anyway, it's in there. So 1/2 is 2 to the -1. So let's use that. Save these two. So let's write 4 as 1. Oh, I was thinking about this and then I wasn't even looking at the problem. Okay, so 4 is 2 to the second power. So I could write this as 2 for 4 raised to the 2x power, and then 1/2 is 2 to the -1 power. So I could write 1/2 as 2 to the -1 raised to the x plus 5. Okay, I'm going to multiply my exponents. So this is 2 to the 4x is equal to 2 to the, I'm going to multiply -1 times x, and then -1 times 5. That would give me -x minus 5. So then I know 4x equals -x minus 5, and I'm going to solve for x. So that's going to give me, let's add x to both sides, so 5x equals -5, divide by 5, so x equals negative 1. Okay, where are we? Part 621. Rewrite each of the expressions below. Your final expression should not contain negative exponents or parentheses. Okay, so we have 5x to the third times negative 3x to the negative second power. So I'm going to multiply 5 times negative 3, multiply my coefficients, that's negative 15. And when I'm multiplying powers, I add the exponents, so I add 3 and negative 2, which would give me x to the first power. And that's it. We have for b 4p to the second q, 4p squared q raised to the third power, so that's just multiplying this by itself 3 times, which you could write out, but I'm going to save time and just use my shortcuts. So that's 4 to the third times p to the second raised to the third would be p to the sixth, and then q to the first raised to the third would be q to the third. 4 to the third, 4 times 4 is 16, and 16 times 4 is 64. So 64 p to the sixth, q to the third. Okay, for C, we are dividing powers, and the shortcut for division is to just subtract those exponents. 3 divided by 1 is just 3, so nothing happens with 3. You're dividing the coefficients, and then you're doing 7 minus negative 1, which would turn into 7 plus 1, so that would be m to the 8th. Um, 622, we have 11 minus the square root of negative 25. So remember that the square root of negative 1 is I. So this is really the square root of 25 times negative 1, and that can be broken down into the square root of 25 times the square root of negative 1, which would give me 5, really plus or minus 5, but I think we are dealing with just the positive root, and then the square root of negative 1 is I. So we get 11 minus 5i, and that's a complex number. You would just leave it like that. Okay, part B. We have negative 4 plus or minus square root of negative, plus or minus square root of negative 36 over 2. Okay, so this is going to simplify to square root of negative 36 would be 6i. So I have negative 4 plus or minus 6i over 2, which can be simplified a little bit more. Negative 4 divided by 2. So when you're, and you have a sum or two numbers that are being added in the numerator or subtracted, you can break it into negative 4 over 2 plus or minus 6i over 2, if that helps, which would simplify to negative 2 plus or minus 3i. Okay, and then part C says 8 plus square root of negative 3. So square root of negative 3 would be square root of 3 times negative 1, and the square root of 3 is an irrational number, so we're not going to write the decimal, we're going to write it in exact form. It's said to write these in the form a plus bi, so exact form would be 8 plus the square root of 3 times I. Okay, 623. For each description, sketch the parabola that matches the given information. So you're going to need some graph paper for 623. And I'm kind of thinking about how we're going to fit this on our paper. Okay, so for part A, it says a parabola with x-intercepts 2, 0 and 7, 0 and y-intercept negative 8. So I'm kind of just sketching this out in my mind, and let's just do a little rough sketch. You don't have to draw this, but it's got x-intercepts of 2 and 7, and it's got a y-intercept of negative 8. So that means it's going to look kind of like this. So let's do our y-axis kind of to the left side of the paper. Okay, x-intercepts are 2, 0 and 7, 0. Y-intercept is negative 8. So here's 2, 0. Here's 7, 0. We don't know the equation. It's just saying to sketch the parabola that matches this information. So you know your vertex is right in between those two, which would actually be 4.5, right about there. Y-intercept is negative 8. So we're just gonna do the best we can. Our line of symmetry would be right here at 4.5. That's where you could fold it, and it would fold right on top of itself. So you could kind of use that to get this point. So there's a point right about there. Okay, that's it for part A. Part B, a parabola with only one x-intercept at negative 1 and a y-intercept at 0, 3. Okay, so think about what this looks like. It's got an x-intercept at negative 1. Okay, it's hitting the x-axis right here, and that's the only place it touches the x-axis, and then it's got it 3. So that means it must be opening upward. So let's sketch that one, maybe kind of over to the right side of your paper, kind of in the middle. Okay, negative 1 is an x-intercept, and y-intercept is 3. Okay, so that means that if that's the only place it's hitting the x-axis, that's the vertex. So I can put that other point over here. I know my line of symmetry is going to be along negative 1. So that's how I'm getting this point right here. Okay, let's go ahead and put x-intercept next to negative 1, 0. And then part C, a parabola represented by this equation, y equals x plus 5 times x minus 1. Okay, we've got an equation for this one. So you should be able to tell me what those x-intercepts are just looking at that. My x-intercepts would be negative 5 and positive 1, and we are going to get the vertex on this one because we do have an equation. So I know it's going to be, this is just a rough sketch, it's going to cross the x-axis at negative 5, and what did I say, negative 5 and positive 1, and I know it's opening upwards because it doesn't have a leading coefficient that would be negative, so I know it's going to be opening like this. Okay, so let's do your part C. You can fit it on your graph if you don't do your x-axis too close to the bottom. Okay, so we've got y equals x plus 5 times x minus 1. So if I replace y with 0, it's already been factored. I get 0 equals x plus 5 times x minus 1, so x plus 5 equals 0, or x minus 1 equals 0, using zero product property. So if I subtract 5, I get x equals negative 5. If I add 1, I get x equals 1. So that's going to be negative 5 and positive 1. So I know my vertex is going to be right in the middle there, and that is the line x equals negative 2. So I'm going to find f of negative 2, plugging in negative 2 for x, so negative 2 plus 5 and negative 2 minus 1, which would give me 3 times negative 3, which would be negative 9. So I have negative 2, negative 9 is the vertex. Okay, so then that would look like this. Okay, for 624, okay, we are actually not going to do 624. We're going to do 5-128. I did this last year. It's a good problem, and it's related to something that's coming up. In 127, you found the solutions to this quadratic equation. The roots of a polynomial function are the values of x such that f of x equals 0. In other words, those are the x-intercepts. You have seen that solutions to equations can be real or complex. In other words, you could have imaginary numbers, so it follows that roots can also be real or complex. Compare and contrast what happens with the graphs and equations for the three cases in parts A through C below. Okay, A says to sketch the graph of f of x equals x plus 3 squared minus 4. Use the graph to determine the roots. So let's work that out on a regular piece of paper, and then we'll sketch it with graph paper. So I'm going to replace y with 0, and then I'm going to work backwards and solve for x. So plus 4 on both sides is going to give me 4 equals x plus 3 squared, and then I'm going to undo the squaring. That's going to give me x plus 3 equals plus or minus 2. Subtract 3 from each side. This one could have been factored with an area model, because I'm seeing right now I'm getting integers for answers. So those two answers would be negative 3 plus 2, which is negative 1, and then negative 3 minus 2, which is negative 5. So those are my roots. They are real, and they're my x-intercepts. So let's think about what this is going to look like. It's going to hit the x-axis at negative 1 and negative 5. And I know it's going to be opening upwards because there's no leading coefficient. That would be negative. So it's going to do kind of like this. And I'm going to, let's just go ahead and do that part right there. Okay, so let's do for part A. I'm going to put my x-axis kind of high on the paper because I'm using a new sheet of graph paper, and I know it's opening upwards. So I'm really more interested in the vertex and the two x-intercepts than anything. So my roots were negative 1 and negative 5. Okay, x-intercepts. So I know my vertex is going to be along the line of symmetry, which would be along the line x equals negative 3. So let's quickly plug in negative 3 and do f of negative 3. So that would be negative 3 plus 3 squared minus 4. That's 0. 0 minus 4 is negative 4. So negative 3, negative 4 is my vertex. And I'm going to graph that. 1, 2, 3, 4. And I want you to see the connection here. This equation was f of x equals x plus 3 squared minus 4, and look at where that vertex is. The vertex is at negative 3, negative 4. This is written in a way that you can see the vertex. So that is going to come in very handy as you move forward with parabolas. Okay, part B says to sketch g of x equals x plus 3 squared and find the roots. Okay, so the roots are the x-intercepts. So I replace y with 0, solve for x, undo the squaring. That gives me 0 equals x plus 3. Subtract 3 from each side, x equals negative 3. So it's only going to have one x-intercept, at negative 3, 0, and there's no negative leading coefficient. So rough sketch, it's going to look kind of like this. So I'm going to sketch that for part B. Let's see. Okay, so my x-intercept is negative 3, 0. The only x-intercept. I know it's opening upward, so I'm just going to do this, because this doesn't have a multiplier. It's not being stretched or shrunk vertically. So basically it's the graph of y equals x squared This is g of x equals x plus 3 squared. This is the graph of y equals x squared shifted 3 to the left. Remember, I was saying this at some point that you would think when it's in parentheses, it's going to affect the graph horizontally. That plus 3 is going to move it either left or right. You would think plus 3 would move it to the right, but it actually moves it to the left. And we just figured out why. We solve for our x-intercept. We could plug in a bunch of points. We could see it that way, but it's important to make those connections. Okay, C says to sketch h of x equals x plus 3 squared plus 4. Can you determine the roots by looking at the graph? Okay, so if I were to solve this and find the x-intercepts, can you tell me what the vertex is before we even get started? Remember, this one up here had a vertex of negative 3, negative 4. What do you think the vertex is for this one? Okay, let's find out. Subtract 4 from each side is going to give me negative 4 equals x plus 3 squared. Undo the squaring, we get x plus 3 equals 2i plus or minus 2i, and then subtract 3 from each side, so x equals negative 3 plus or minus 2i. If I graph this, I don't know where my x-intercepts are. I don't know where that is on the number line. So do you see where you're going to need this vertex form? So if the vertex of f of x was negative 3, negative 4, this also has x plus 3. So this is going to be a negative 3 for the x coordinate, but instead of negative 4, it's going to be positive 4. So my vertex is negative 3, 4, and this is just the graph of y equals x squared, shifted 3 to the left, just like the previous one, and 4 up. So 3 to the left, 4 up would look like this. Okay, and I'm just going to go over 1, up 1 in each direction, over 2, up 4 in each direction, because that's what y equals x squared looks like. Okay, that was h of x equals x plus 3 squared plus 4. And the reason it has imaginary solutions is because it's not hitting the x-axis. So it has complex, we would say it has complex roots. So that's it for 5.128. It was to sketch these and look at the roots. Here you've got 2 real roots. Here you have 1 real root. And here you have no real roots. You only have complex roots. Okay.